So last week we talked about aromatic compounds. We discussed the fact that when we have a cyclic compound that has its cyclic system completely conjugated, that is, the atoms are hybridized such that there's leftover p orbitals in which the electrons can delocalize. And if we have an odd number of electron pairs within that conjugated cyclic system, we get aromaticity. If we have an even number of electron pairs, we actually form a compound that's much less stable than we expect. We get anti-aromatic compounds. So even though these aromatic compounds are quite stable, they can still be reactive. Only we have to soup up our reactants because they won't react with normal electrophiles. We need quite powerful electrophiles because the aromatic compounds are such weak nucleophiles. Nevertheless, we can do so. So what happens? Let's go back a bit. Let's take a look at what happened on when we did electrophilic addition of alkenes. So in this reaction, our alkene is our nucleophile, our bromine is our electrophile, and the nucleophile attacks the electrophile. We get subsequent reactions, and we get addition of bromine, Br2, across the double bond. When we try a reaction of an aromatic compound like benzene with molecular bromine, nothing happens. Even if we heat the reaction up, we get very little reaction. However, we can get a reaction by throwing in Lewis acid, and the Lewis acid acts as a catalyst. We don't need a lot, but we just throw in some Lewis acid. It will soup up the electrophile, and the electrophile then is strong enough to react even with a weak nucleophile such as benzene. However, we don't get addition of the bromine in this case. We get substitution. One of the hydrogen atoms on the aromatic ring gets replaced by a bromine. The other product, of course, would be simply be, in this case, HBr. So recall the halogenation of alkenes. What happened there? The alkene is the nucleophile, and the bromine is the electrophile. Even though bromine is nonpolar, it's very polarizable. So as a nucleophile approaches bromine, it disturbs the electron cloud that forms the sigma bond between the two bromine atoms, and we get an induced dipole. One of the bromines becomes slightly positive in nature, the other bromine becomes slightly negative, but this bromine, the one that's slightly positive in nature, can now act as an electrophile and get attacked by the nucleophile. The reaction is such that we get a nucleophilic attack on the bromine, and at the same time we get loss of bromide, and another pair of electrons attacks the other side of the alkene, so we get this bromonium ion intermediate, and we also kick off a bromide. So that's the first step in the reaction, and then our nucleophilic bromine attacks the bromium ion. We have a new nucleophile electrophile pair. This is actually a rare reaction where we have a nucleophilic attack followed by another nucleophilic attack. And we get our products, and this is just indicating that we get the other enantiomer of the product. What happens in the case? What's happened thermodynamically in this reaction? We start off with our alkene and our bromine, and the first step in the reaction forms the bromonium ion. Now, both of these should be the bromonium ion. They should actually be at the same energy level, but it has two options at this point. Bromide could come in and act as a Bronsted base and pull off one of the protons, and then the electrons in that carbon-hydrogen bond could reorganize, form a double bond, and then we could kick off this other reaction and we could get a substitution-like reaction. This reaction is thermodynamically favorable. It gives off about 11 kcals of energy. However, it has a fairly high activation barrier. The other option for this bromonium ion intermediate is over here where we can get addition. In this case, the bromide acts as a nucleophile and attacks one of the carbon atoms, and we get addition. So the first bromine added as an electrophile, we got the bromonium ion, which was electrophilic still. The other bromine became a bromide and acts as a nucleophile, and we get addition across the double bond. This is considerably more favorable thermodynamically, and it gives off 27 kcals per heat. And as it turns out, it's also kinetically favored because the activation barrier for this pathway is much less than the activation barrier for the substitution reaction. So this reaction is both kinetically and thermodynamically favorable, so we get very little, if any, of the substitution product, and we only get addition. Let's take a look at what happens when we do a halogenation reaction. We can substitute one of these hydrogen atoms with chlorine or bromine quite easily. All we need is a Lewis acid catalyst. If we're using chloride, we would use a Lewis acid catalyst with chloride. If we want to use bromine as a reagent, we use a Lewis acid catalyst which contains bromine. Now, one of the things that happens in this reaction is that the bromine is not the active electrophile. The Lewis acid catalyst starts off as being the strongest electrophile, and it reacts actually with bromine. Bromine adds to the Lewis acid catalyst, and we now have this activated compound, which we see over here. Some people argue that we get full transfer of bromide to the Lewis acid, and we get a bromonium ion in solution, but more people favor the fact that it's likely this complex that is the reactive electrophile in the next step of the reaction. So what happens in the next step of the reaction? Well, in the next step of the reaction, we now have our activated compound, which is our electrophile, and it's such a good electrophile that even a weak nucleophile like benzene can react. So the electrons in the pi system just reorganize and attack the electrophilic complex, and we get a bond between this carbon atom and this bromine, and we kick off FeBr4. We get a sigma complex or an arenium ion intermediate. As we'll see in a little bit, this positive charge is delocalized, so this is somewhat stable, and it's not as endothermic as we might expect. Even though we've broken up the aromaticity, this is going to be higher in energy than the products, so it's going to be an intermediate reaction. It then reacts with the FeBr4, acting as a base, pulls off the proton on the arenium ion. We get a reorganization of the electrons in the carbon-hydrogen bond to reform a double bond. When that double bond reforms, we get our aromatic system back. We also regenerate the catalyst, and we've given off the elements of hydrobromic acid. So we have two steps in this reaction. The aromatic ring attacks the electrophile, forming an arenium ion intermediate, or a sigma complex. And step two is the deprotonation of that sigma complex. Let's take a look at the thermodynamics for this system. And here we have a reaction profile. Same thing happens. We have our aromatic compound, we have bromine, we have our Lewis acid catalyst. Notice in this case we didn't form a bromonium ion. We actually show the positive charges being on the carbon. One of the reasons for that is this is considerably stable carbocation, and the charges on the carbon, because it can delocalize, as we saw earlier, over the whole of the ring except for the sp3 hybridized carbon. So in order for addition to occur, we would then just get an attack of the bromide onto that carbocation, and we would get these types of addition products. As it turns out, this reaction is not very favorable energetically, because we've broken up the aromatic system, and even though we get a little bit of energy back in the formation of the carbon-bromine bond, it's not enough to make up for the breaking of the aromatic system. So this is enthalpically disfavored by about 9 kcals per mole. On the other hand, if the same intermediate can react with our Lewis acid adduct, the FeBr4, acting as a Lewis Bronsted base, pulling off this proton and reforming the double bond, we get a substitution product and we get our aromatic system back. And this reaction in this case is enthalpically favored by about 11 kcals per mole. We also formed the hydrobromic acid. So we get our addition to the aromatic compound, which is disfavored because the product is no longer aromatic. But we get that aromatic energy back if we undergo a substitution reaction, and we don't get that energy back if we undergo the addition reaction. So the addition is favored for thermodynamic purposes, and it's probably disfavored kinetically as well. So we have a number of electrophilic aromatic substitution reactions that we see here. We've already discussed halogenation, and we can also get nitration, and they all go through the same type of mechanism, which we'll talk about in the next video.